So sorry, I could not log in, so I was concerned and I had to write an email why it is not possible. And that it was written that it's now 10:30 instead of 10. Okay, anyway, now I'm in, it's fine. Can we start or when we are already late?
We are live. You can start, please.
Yes, if you please load up the PPT. I don't see anything. Could the manager load up my PPT?
PPT is my screen is visible to you.
No, it is nothing visible to me.
Oh.
Okay, now I can see your presentation.
Sir, we are live. You can start, please.
Yes, if somebody.
Okay, thank you.
If somebody would download mine, now I can see. I could see yours from Mr. Gupta.
Okay, so I am planning to give some brief overview on the determination of ground motion parameters for earthquake resistant and earthquake safe design of large dams in particularly in Himalayan region, which is that the seismic safety of dam is very important because the society cannot bear the losses and the suspension of the services being derived from a dam. And even if there is no risk to the population downstream, still the various uses to which we are putting a river valley project are so important that there are no alternatives to those dams is very, very important. The design of dams has developed by trial and errors for a long time. And in the earlier design, the seismic aspects were not included. It was only in 1924 for the first time that seismic forces in the design were introduced in a very after the Kwanto earthquake in Japan, and the seismic coefficient was defined in a ad hoc manner, and this was taken to represent the seismic forces as 10% of the weight of the dam. So the 0.1 was taken as the seismic coefficient multiplied by the weight that was taken as the horizontal forces along with the other static forces to see the seismic stability of the dam. Dams in India is still based on largely on the static stability of the dam under the seismic forces defined by seismic coefficient multiplied with the weight of the dam and other static forces which are continuing permanently without earthquake also are taken simultaneously with this static earthquake force. And the concern is only overturning stability of the dam against combined effect of these forces. The provisions for seismic coefficient in India are defined in the Bureau of Indian Standard Code, which was first published in 1962 and has been revised several times, but there has been no fundamental change in the philosophy of design, only with the occurrence of some damaging earthquakes in different parts of the country. Time and the most recent code, which has been brought out in 2016, divides the country into 4 seismic zones, and for each zone, they give the recommendations or provisions for finding the seismic coefficient, alpha H, in terms of a zone factor, the importance factor of the structure, and a response reduction factor to take into account the reduction. And they give a standard normalized spectral shape. So this is the methodology being used largely along with the design provisions given in another code for concrete dam, that is IS 6512, criteria for design of solid gravity dams. And the entire design is governed by this simple equation in which the sliding of a block of the dam along a pre-selected horizontal plane is designed by all the horizontal destabilizing forces. Here, this is the frictional force and this is the cohesion force. So these frictional force and cohesion force are the stabilizing force, and P is all the destabilizing forces acting due to the equivalent static seismic force and the hydrostatic and uplift pressures and silt pressure, and they give different combinations of loads and the factor of safety recommended for various combinations in the against this friction and the cohesion they have defined. So final factor of safety should be just above 1, and the conservatism is inbuilt into the factor of safety against this uh, frictional and the cohesion reduced drastically, and then the final factor of safety is taken as F. So the entire design is based on the frictional resistance and the cohesive force available along a pre-selected horizontal plane. And this is applied with a very, very small value of the seismic coefficient. The seismic coefficients recommended in the code are a fraction of the actual earthquake forces which can be experienced during real earthquakes. So this dam in an explicit way. It is assumed that if this sliding safety is ensured, the dam will be safe. But during earthquakes, the safety of the dam has to be actually ensured against the stresses developed due to dynamic effect of the earthquakes. And the strength of the material of the dam should be able to withstand those stresses, particularly the tensile stresses. The same philosophy is being applied for here. Instead of a horizontal plane at a particular elevation, we see the stability against a circular plane passing through the body of the dam and also through the foundation. So several such sliding potential planes are assumed, and the safety of sliding against all the possible planes of failure is assessed again. Cohesion and the friction. These two factors are the resisting forces. and destabilizing forces are provided by the weight of the dam and the earthquake forces and the uplift pressure that is known as pore pressure. In case of the earth dam, the pore pressure plays very important role, and the disbalance of the pore pressure under fast and drawdown conditions due to the required extent plays very important role. But the stability is again here governed by the Coulomb's law, where the stability is provided simply by the cohesion and the angle of friction. C and phi are the only governing factors in case of both concrete as well as earth dam in case of the traditional design, and the stresses and the dynamic effects of the earthquakes are not taken into account. Ensure the realistic safety had been illustrated long back in case of our Koyna Dam, which suffered a large number of horizontal cracking at this level, these red zones, during an earthquake of 6.5 magnitude, which occurred on 10th of December 1967. So after this experience, that to ensure the seismic safety of dam, it is essential to design and analyze the dam for actual dynamic effects of the earthquakes using the actual earthquake forces expected at the site of the dam, and not the seismic coefficient, which is highly reduced in an artificial way to represent the earthquake forces. So the philosophy of design has to be to stress analysis, or the, in case of earth and rockfill dams, to see the permanent deformations under dynamic effect of the earthquakes. So all the dams in our Himalayan region are in fact are more prone to seismic damage, and this shows the Himalayan region. India is divided geographically into three zones. One is the peninsular India, which is seismically stable. Damaging earthquakes have been experienced, and we have to take care of the design of dams against the expected earthquake forces. Then we have the Indo-Gangetic plains, and the region of these plains adjacent to the Himalayas are also prone to seismic hazard, and the structures there have to be designed based on the true ground motions expected. And then the Himalayas from west to east, 2,500 kilometer length, is having high seismicity. And there are various tectonic features like main boundary fault, main central thrust, and then the main frontal thrust just abutting the Gangetic plains. So these are the tectonic features which are the locations or the sources of large earthquakes. And our maximum river valley projects are located in this zone only. These are this red which I have personally been involved in getting the design ground motion for dynamic analysis, and I will be presenting one typical examples that how we do. This shows the seismicity during last 200 years, and if we see this Himalayas and northern part are these lot of earthquakes have occurred in the past, and we have experienced 4 great earthquakes of magnitude 8 or we have to definitely design all the dams in the Himalayan zone by the dynamic analysis rather than the seismic coefficient, which is not able to ensure and evaluate the seismic safety in an explicit way. So we have to change the design philosophy from stability analysis to the stress analysis under realistic ground motion. And for parameters in terms of the response spectra and the acceleration time histories. Response spectra method are simple to apply, which can be a replacement for the current use of seismic coefficient, because in principle, the response spectra method has been developed in such a simplified manner that they are almost identical in the analysis to the stability that we have to replace the seismic coefficient by the spectral amplitude at the natural period of the structure. And then the analysis can be taken almost in the same way. In case of the gravity dams, we compute the stresses by the beam theory, similar to that in the traditional method, under this seismic force along with other forces. In case of deformation at the crest, using Newmark sliding block method or Makadashi's seed simplified method to estimate that what deformation may be. So at least for the preliminary design also, we have to carry out the dynamic analysis based on these simplified methods, which are as simple as the traditional pseudostatic method. And then in case of important dams or where methods, we have to go by detailed dynamic analysis using time history methods, or even in some cases, if it is warranted, we may have to go for nonlinear analysis. So the design parameters for this purpose have to be defined in terms of the design response spectra and the acceleration time histories compatible to the design response spectra. And for estimation of these parameters, we are following the guidelines brought out by our known as the National NCSDP guidelines. NCSDP stands for National Committee on Seismic Design Parameters. And these guidelines are more or less in consonance with the Icold Bulletin 140 with slight modifications. So I will show that how we are applying these guidelines with one typical example of a dam site in the Arunachal state of India, that is the easternmost part of the Himalayas, and a dam I analyzed there, and I will show that what level of spectral amplitudes and accelerations can be experienced. So these NCSDP guidelines, which we are following, recommend that we have to estimate the design parameters in a site-specific way using deterministic as well as the probabilistic approaches. The design motion by comparison of both, and if the results from the two methods differ largely by very large margins, then we have to rationalize the results, because the deterministic approach involves a lot of subjective decisions, and which at times may not be scientifically rational. So the probabilistic approach provides a benchmark to compare the design parameters from a comparison of the results of both the deterministic and the probabilistic approach. In the probabilistic approach, we first identify the various seismic sources. The earthquakes in those sources can affect the site of the dam, then estimate the seismicity of each source and evaluate the ground motion probabilities and compute the hazard spectra, which are known as the uniform hazard probability of accidents at all the natural periods. So this is the region where I have considered the dam. This is the dam known as NAFRA project, which I worked on about 4 or 5 years back. And these are the various earthquake generating faults. So this northeast region of India is geologically, tectonically, seismically is a very complex region because it is being under thrusting from two sides. This side is the Burmese subduction zone. This is a Himalayan syntax where the Himalayas ends and take a eastward turn. Then there is a Shillong plateau region, which is in between the plate boundaries, but due to the compressive force acting from two sides, this also is a seismically active region. And we had a great earthquakes in 1897 with magnitude more than 8.2. That time it was estimated as 8.7, but now 2. So if we see the seismicity, this entire area of about 7 degree by 7 degree latitude longitude is studied with the epicenter. So there is no place where there is no seismicity. So this is a highly seismic, and this is the site where we have to estimate the design parameters. So I told the first step is to make the various source zones. So these are the source zones which are tectonic grains and the occurrence rate of seismicity as well as the maximum magnitude which can be expected. So variation in the level of seismic potential and the changes in the tectonic characteristics. We divided this region into 15 different source zones, and these source zones are names are tectonic features that these source zones is the first step, and then we estimate the seismicity for each source in terms of the occurrence rate defined by the Gutenberg-Richter relationship, where log nm equal to a minus bm. The nm is the cumulative number of earthquakes with magnitude greater than equal to m, and a and b are the constants which are estimated by regression analysis of the past seismicity data, which are summarized here. So there were a big database of more than 4,000 earthquakes used for this, and we defined this Gutenberg-Richter relationship for each of these source zones by considering the completeness of the earthquakes, because very small magnitude earthquakes are their rates are not increasing due to lack of recording of small earthquakes for the olden periods when instrumentations were very sparse. So this for source zone Richter relationship. So we have used this relationship for each source zone to define the occurrence rate for different magnitude of earthquakes. Then we select a attenuation or ground motion prediction equation, which is used to compute the what ground motion can be expected, and this has to be region specific. As we don't have adequate number of recorded strong motion data to develop our independent, I used the limited data available to select the most appropriate equation from the published relations. And using that database, I applied the criteria in terms of the statistics of the residues between the recorded data and the predictions from the selected equations. And from that criteria, I found that the equation by Campbell and at that time, now we have 2014 also, but that time 2008 was the latest relationship, was found to be best. So this dotted curve shows the statistics of residues, and solid curve shows the ideal curve which should be obtained. So they are both very close. And then we used a different equation for the Burmese subduction zone, because the Himalayan and the other part of this region are shallow crustal earthquakes, whereas in the Burmese subduction zone, we have deep subduction zone earthquakes. So they have a different ground motion characteristic. So this equation the Burmese subduction zone earthquakes was used for that source. Then then coming to this deterministic approach, in that we consider only limited combinations of the maximum magnitude and minimum distance at which they can occur on various tectonic features in the region, and select the controlling combination of maximum magnitude and distance, which is the combination. And for that, we compute the response spectrum with 5% damping from the selected equations for ground motion prediction. And that is known as the target response spectrum obtained by the deterministic approach. But in case of the probabilistic approach, we consider all the expected earthquakes with different magnitudes with their occurrence rates to find out the target response spectrum. So we consider rates. Lambda n is the occurrence rate of magnitude mj in the nth source. And this Qn is the probability of exceeding a spectral amplitude due to magnitude mj distance Ri from the selected ground motion prediction equation. So by combining all these probabilities, we define a total probability for the exceedance of different spectral amplitudes, and from that we define a uniform hazard response spectrum with 5% damping, which gives us the target spectrum by probabilistic approach. So for this dam site, for the MCE condition, that is a maximum credible earthquake, because we have to give of earthquakes. One is the design basis earthquake DBE level of ground motion parameters, and the other is the MCE, maximum credible earthquake level of design parameters. And the design philosophy is such that the dam and other appurtenant structures should be absolutely safe against the ground motion represented by the DBE. But under MCE, considerable damage is acceptable, which doesn't jeopardize the water retaining capacity of the dam. So only we have to see from the dam, but severe damages which doesn't impair the water retaining capacity of the dam can be accepted under the MCE. So for MCE condition, these are the deterministic. This blue curve shows the deterministic target response spectrum, and red one shows the probabilistic target spectrum. Now they are not close to each other. They are differing extents. So as per our NCSBP guidelines, here we took a weighted average of both the spectra to define the final target spectrum. Similarly, this is the target spectrum for the DBE condition. And for this target spectra, we then generate the acceleration time histories, which are these spectra of this time history closely, and therefore these design accelerograms are known as spectrum compatible time histories. There are two ways to do it. We can generate these time histories compatible to the target response spectra synthetically by artificially, or we can select the real time histories of earthquakes and modify those to match the target response spectra. If we have to, then we have to go by a set of recorded time histories modified to be compatible with the target spectra. but for simple linear analysis, synthetic time histories can also be used. These are the horizontal and vertical time histories for use in detailed dynamic analysis. And from these time histories, because the target spectra are defined for a damping, and these time histories are then utilized to generate the response spectra for several different damping ratios of 2, 3, 5, 7, 10, and 15% of critical, because we may need the spectra for simplified analysis with different damping values. So these are the spectra and the time histories provided in our site-specific reports. And this one example I have shown for the Northeast India. Now, as this sort of detailed analysis cannot be done quickly and readily for each and every project, and particularly for the feasibility state and initial state design of dam. So it is essential that we develop the hazard maps which can be utilized to generate such utilized to see the stability of the preliminary design of the dam. To illustrate that, I have carried out one analysis where I have generated such a hazard spectra and how those can be utilized to generate the target spectra for the northwestern Himalayan region. This is the this is the Indian territory, and this region I considered to generate the probabilistic similar to that for a single site. I considered these various seismic source zones, defined their seismicity, and then calculated the hazard in terms of the response spectral amplitude at a grid of closely spaced locations covering the entire territory, and obtained the hazard maps for different natural periods spectral amplitude. So this is these two maps are for the DBE condition and MCE condition. Then the next two are for the spectral amplitude at 0.1 second period, spectral amplitude at 0.2 second period, spectral amplitude at 1 second period, and the PGA and the spectral amplitude at 0.2 second and 1 second period can be utilized to generate the response spectrum for any location from such maps. So that can be done very readily. And this equation has been SCE 07 code, but there are some modifications to suit the our region of interest. And using this equation, we can generate the design spectra, and those are compared with the standard spectral shapes given in our BIS code, and based on the ASC formula and the proposed formula in our this study. So they differ slightly. Design spectra readily, which are a sort of first cut for the site-specific analysis, and these can be used with the simplified dynamic analysis using these response spectral amplitude to find out the stresses at different elevations in the dam, or to find out the permanent deformation in case of earth dams, and to see whether these are within the permissible limits. So this is the recommendation that we have to give up the traditional pseudostatics on spectral amplitudes to find out the stresses or the permanent deformations in concrete and earth dams respectively for their preliminary designs. And if they satisfy these dynamic stability requirements, the static stability is automatically ensured, because the static stability is analyzed under much reduced seismic coefficients, and that doesn't automatically ensure the damage due to tensile stress, but the stability against tensile stress will automatically govern the stability against sliding and overturning. So we have to carry out detailed dynamic analysis for final design and can develop such zoning these hazard maps for preliminary design. And then we should be able to ensure the seismic safety of our dams explicitly and in a more realistic way. I stop here and thank you all.
Okay, it was a very nice presentation. Okay, for me it's very interesting. Thank you very much, and it was also very
Thank you,
clear.
sir.
I must say. Okay, thanks a lot.
So,
I have
Martin,
no question. Yes.
Martin sir, you want to try or we can share?
No, he has a question.
You download your PPT, which I send you.
Yes, I have. I'm sharing. Screen is visible, sir?
Yeah, now it comes.
Okay.
Can you put on presentation? Yes.
Yes.
Okay, now finally it works. Sorry for this, let me say, this technical problem, which we have faced by logging in and having received some strange message. So good morning, ladies and gentlemen. This is the overview presentation which I was asked to deliver. The subject is a seismic safety evaluation of existing dams. I have written a paper, and the paper should be included in the proceedings of this symposium. First, I would like to mention, okay, have been the chairman of the Icold Committee on Seismic Aspects of Dam Design already for more than 20 years. So since 1999, we have about members from about 35 different countries. I have been working with company AFRI, Switzerland. Before the name was Beury, and just last April we were taken over by a Swedish company, and therefore the name Beury has changed to AFRI. So therefore I'm giving my relationship here with AFRI. That is just, and I think we are also here in India. Okay, next please. Next slide. Okay, yes. Okay, let me give first an overview. Dr. Gupta, he has also given some overview, so there is some small, let me say, duplication, but I'm discussing it from a point of view of dam engineering. Please note that dams were actually the first structures which were designed systematically against earthquakes. Okay, Dr. Gupta has mentioned the earthquake in Japan, the Kanto earthquake, and where the seismic design which was introduced was used for buildings, not for dams, but and they were only used locally in Japan, not worldwide. These codes which were proposed in Japan at that time, but in the case of dams, there have been, let me say, methods proposed which have been applied, which I would say universally. If we look first into concrete dams, it is a method which was proposed or developed by Westergaard in the 1930s for Hoover Dam in the US. And he proposed there this also pseudostatic method. And This pseudostatic method, which Dr. Gupta has mentioned, found worldwide acceptance and was used until the late 1970s, and in some parts it is still being used. And the method, this pseudostatic method for concrete dams, accounts for the inertial effects of the dam, and it also accounts for the hydrodynamic pressure, and the seismic hazard was represented by a seismic coefficient of 0.1. Okay, so it was even mentioned that we thought that the value of 0.1 was used more or less universally, irrespective of the seismic hazard. But as I've seen in a previous presentation for Koina Dam, actually a value of 0.05 was used, even lesser than what has been used usually on internationally if we didn't know anything about the seismic hazard, which was a standard practice. Now for embankment dams, similar, the first dynamic analysis was done by Mononobe et al. Also about the same time, 1936. So these methods for pseudostatic method were introduced about 85 years ago. It's already very old method, and also in the embankment dams there was a pseudostatic slope stability analysis and also the use of a seismic coefficient of 0.1 to 0.15. Okay, what is the result of a pseudostatic method of this low acceleration? The earthquake load case practically never become a governing load case. So if you did your design of a dam and afterwards you checked the safety of the dam with a pseudostatic method, usually the safety factors were okay, probably in almost all cases. So nobody really worried much about earthquake safety in a design because it was satisfied. Now, please keep in mind that Dr. Gupta has also pointed out that, I'm happy to hear that also from India, that the pseudostatic method and the characterization of the earthquake hazard by a seismic coefficient, these are outdated methods and shall no longer be used, especially in area of high seismicity, like for example here in the northern India in the foothills of the Himalayas. Next one, I will discuss that also later. Next slide, please. And yes, okay. Now, just what I mentioned, seismic. My subject is seismic safety of existing dams. We have to keep in mind that most existing dams were designed against earthquakes using methods of dynamic analysis. That means a pseudostatic method and seismic design criteria. That means the earthquake hazard was represented by a seismic coefficient of 0.1 at most dam sites in the world. And today, and I must say, also my Icold Committee on Seismic Aspects of Dam Design, we consider this method, which was very good at the beginning in the 1930s until a few decades later. But now we know this method is obsolete or even wrong, and I will show some examples. Therefore, because of these dams were designed with this outdated method using, let me say, seismic safety criteria, which also have changed. So therefore, it is not known if these existing dams actually satisfy today's safety criteria. So therefore, my Icold committee, we have always strongly recommended people to look into the seismic safety of their existing dams, and several countries have taken that up. I will discuss that later. Okay, please also keep in mind that also in connection with, let me say, climate change and so on, people think, some people who are not familiar with dam safety, they feel people will just adhere to such values. It is wrong. Basically, we have to keep in mind that the seismic safety of existing dams must be checked repeatedly during the long lifespan of dams. We have heard yesterday, apparently there are some dams in India which are more than 1,000 years old. We don't have that many old dams in Switzerland. Okay, next one. So what have been the developments, just to give you a brief overview, which have taken place during the last decades. Number one, originally there has been a change from a pseudostatic analysis to dynamic analysis of dams. Okay, so that today for large dams people do a dynamic analysis. Number two, there has been a change from a characterization of a ground shaking by a seismic coefficient to what we call today safety evaluation earthquake ground motion parameters, which are, for example, the acceleration response spectra or uniform hazard spectra, which were presented by Dr. Gupta. Number three, we also have to keep in mind, in the past, basically people only looked into the ground shaking hazard from earthquake, but basically today we have to pay attention that earthquakes are so-called multi-hazard events. It is important. Dr. Gupta has just shown the ground shaking, but today, and you know from the incident, for example, in Shamoli, that if you have a strong earthquake in this Alaknanda River area, or already a moderate earthquake, you may trigger very huge mass movements, like with ice and rock falls in India a few days ago. So therefore, these events can be much more serious than any ground shaking events. So we have to look in all aspects. So this is a very important issue, and please keep that in mind. We must look into all possible hazards, and I'm sure if there would be an earthquake, now people say it is climate change, but such kind of events would be triggered very easily by earthquakes. Okay. Number four, we also have changed from what we call safety factor concept, okay, to more rational seismic performance criteria, which are mainly based on inelastic seismic dam deformations, which applies for both, for embankment dams and also for concrete dams. For concrete dams, we also look into the sliding stability, but the sliding stability shall not be the sliding stability just between the a sliding surface at the contact between the foundation and the mass concrete. But for dams, we know we have dynamic amplifications towards the crest, which is very significant. So therefore, actually blocks near the dam crest are much more critical than the foundation stability. And basically nobody is looking, until now, has been looking into the stability of blocks in the upper portion of a dam, which are more critical than the foundation sliding. Okay, number five, we have to leave, let me say, in the past, we looked only into the safety of a dam body, only into that. But today, we have to look in the safety of a dam body, plus what we call safety critical elements. The safety critical elements are elements which have to be functioning after an earthquake in order to control the reservoir level. And this is basically done by spillways and low-level outlets. In Switzerland, I would like to promote here also the idea of low-level outlets. It is very essential because it allows you to lower the reservoir, and by lowering the reservoir, we can reduce or we can increase the safety of our dams. If the reservoir is empty, there is no threat to people living downstream. Okay. In addition, we also have to look into the abutments, especially for arch dams, and we have to look in the reservoir slopes, as I mentioned, the recent incident in India, because reservoir slopes, if you have landslides, they can block intakes and they may create large impulse waves. I must say the lesson which I personally have learned from this incident here recent in Chamoli in India is that if you have this kind of, let me say, extreme event, it will transport in the mountainous regions, it will transport a huge amount of debris, not floating debris here, but it is a sediment. And people, I must say, in these dams, they have usually, if you look into it, flood safety, you assume this water is clean. But actually here, what has been coming into the reservoir was basically, most was sediment. Okay, so therefore, these let me say, reservoir slopes, and even further, as this Indian case has shown, you have to look even beyond the reservoir slopes. Okay, next one. Okay, why do we need safety evaluations of existing dams, and why do we have to do that periodically? I mentioned already at the very beginning the service life or the economical life of a dam can be very long. I think for embankment dam, it is built of natural material. I think it can survive hundreds of years if it is well maintained. Okay. For concrete dams, I think they can also survive a long time. The oldest Swiss concrete dam, which is the oldest one in Europe, it is now 140 years old, and the concession has been extended. It will easily reach 200 years. So what has been written in a recent UNU report here, that there is a huge threat of the people living downstream of aging dams. I think these people, in my opinion, don't understand the problem properly. It is not basically the aging of a dam which increases the risk. It is more the people living in a downstream area of a dam has increased rapidly. So therefore, the risk, let me say, in the case of a dam failure, has increased substantially, not due to, let me say, aging. Certainly in Switzerland, we would not, we would fully disagree with that report. 50 years is nothing. The average age of the Swiss dams, which are all considered as safe, is already 75 years. So if somebody talks about 50 years service life, they don't understand much about engineering. I would just like to mention there is a new railway tunnel under construction, Brenner railway tunnel between Austria and Italy, and there already now in a design specification, the service life has been specified as 200 years. So the design is based on 200 years, and dams, I would say, last longer than tunnels. So we have much longer service lives if they are well maintained. Okay, so we do safety evaluation if new information on seismic hazard will become possible, as Dr. Gupta has presented, and new information is available on seismotectonics compared to the past. Secondly, when a dam has been subjected to strong earthquake ground shaking, there is a need to check the safety of a dam. Also, when there are new seismic design criteria are introduced, as I will present also here, for example, from Icold, that we do not only have to look into the ground shaking, but we also have to look into other aspects, and we have to look into spillways, we have to look into slopes, which before nobody looked at. Number 4, if new seismic performance and safety criteria are introduced, which is also being done, it's basically introduced in the Icold Bulletin 148, which has been published in 2016. If new dynamic methods of analysis are introduced, let me say, change from a pseudostatic to linear dynamic, but now we come more into non-linear dynamic analysis methods, like dynamic stability methods. Next one, if the seismic vulnerability of a dam has increased due to modifications, for example, hastening, or also due to aging. Aging is basically also a problem of more a problem, I would say, from the hydromechanical equipment. Next one, if there have been changes in risk classification of dams, which may be done in a country. This is a quite a delicate issue. Risk classification. Okay, there is no unique classification, and there are big differences. It is very important. And the last point is, if the seismic risk has increased, for example, due to the number of people living downstream of a dam having increased, and due to economic development and so on. Next one, please. Next. Okay, I would just like to make some short promotion to my committee on seismic aspects of dam design. It was created in 1968. Okay, already 52 years old. There have been a number of bulletins which have been published in the field of earthquake safety of dams. And I would just like to mention a few of them. The first one, 112, is neotectonics and dams. That means active faults in dam foundation or potentially active faults in footprint of dams, which is concerned with the seismic hazard. It's not with ground shaking, but it is with faulting. Faulting can be much more serious than ground shaking. Number 237 is called reservoirs and seismicity. It is concerned with reservoir triggered seismicity. It is also concerned with the hazard. And I would say the initiating event for such a bulletin, of course, was also case of the 1967 Koina earthquake, where it is assumed, or let me say, many people assume, or it is suspected that this earthquake was triggered by the reservoir. Okay, some people do not agree with that, other people are of other opinion. Number 3 is a built-in 148 that is concerned with selecting seismic parameters for large dams. It specifies the seismic design criteria. It is important here because if we do not have seismic parameters or let me say design criteria, we cannot do any analysis. The basic of any analysis is of course the seismic design criteria. Okay, we have a bulletin 52, it's an old one. Actually, it was written by Clough and Stienkiewicz and Seed, you know, for those who like to do dynamic analysis and finite element analysis, Clough and Stienkiewicz are two of the three inventors of the finite element method. And these people basically have worked in a dam on dam problems when they introduced that method. Okay, so dam engineering has been, let me say, the starting point, I would call it like that, of a finite element method. Okay, next one, there are some design features of dams to effectively resist seismic ground motion, which is concerned with the conceptual design. If you follow this criteria given in that guidelines, you will arrive at the dam which basically will be seismically safe, which if you have to do then the safety check, I must say if you follow this criteria, basically your dam in most, especially smaller one or medium height dams, will be safe. Okay, and there are some design criteria on appurtenant structures, and there have been some guideline on the inspection of dams. Okay, next one. So that is what my committee has been doing in the last year. So it has covered various aspects, I must say most of the important aspects of the seismic safety of dams. Next one. Okay, just let me say something quickly about Switzerland. Existing dams, large dams in Switzerland, just to give you an idea. The average age is about 75 years, and we have 202 dams, which are mainly all concrete dams or run-off river power plants. We have only a handful of embankment dams, which is different from other countries. But in mountainous regions, okay, some concrete dams seem to have some advantages. Next one. Just to give you some view of Switzerland here. Okay, this is Grand Dixence Dam, which is still the world's highest gravity dam with 285 meters. Until about 7-8 years ago, it was the world's highest concrete dam. And as you see, this year it will celebrate the 60th anniversary. No very high dam has been in operation for that long time. Okay, but in India you have a Bakra dam, of course, which is also almost of similar age, which is a little less high than the Grand Exhaust dam. Next one. Okay, we see here it has some kind of polygonal shape. If you look to crest, next one. Okay, you see the dam crest. The special feature of Swiss dams is a wide dam crest. It is 15 meters. If you cannot lower the reservoir, you must have a very thick crest. This is a requirement from a military. It required that the dams must be able to resist the largest conventional weapons, bombs, let me say 10 tons of explosives. So therefore, the dam crest here, as you can see, is at least 15 meters, is very wide. So for dams where you cannot lower the reservoir within a short period, the Swiss dams are extremely thick at the crest. It's originally due to military requirement, not for structural requirement. Next one. Okay, I would like to mention this is the same dam. We also have a lot of mountains. Of course, in the Himalayas, the mountains are 2,000–3,000 meters higher. These are about 3,000 here around this Grand Dixence, which is at about elevation 2,300. But I just want to mention these dams are built also in difficult topographical and climatic conditions, and during construction here, people could only work during summertime. And you see here, you also have the problem of glaciers, and people have investigated the effect of avalanches in a reservoir and impulse waves created by such incidents. Next one. Okay, this is Mauvaisin Arch Dam. It belongs to our company before. It is 250 meters high. It was completed in 1956. It's 63 years old already. Okay, as you see here, okay, this picture a few years ago, but you see the concrete looks quite fresh. here in winter time. Next one. Okay, characteristic is that let me say, the, the, the reservoir rim is quite steep. So it was possible to increase the height of this dam. Next one. The original height of this dam was 237 meters, and in 1991, the height was increased by another 13.5 meters. And because the dam crest was very thick, 60 meters, it was easily to increase the height by 13 meters without having to strengthen the shell. Because as I mentioned already, for dams with large reservoirs, the dam crest, because military reasons, had to be very thick. Next one. Okay, a few examples of dams in highly seismic regions. Next one. You know, the biggest dam in the world, or the largest dam, is the Usoy Dam in Tajikistan. It is 650 meters high, twice as high as any man-made dam. It was created by a huge landslide, and this landslide was triggered by a magnitude 7.3 earthquake 110 years ago. So as I said, if you have a big earthquake like in the Himalayas, you will have thousands of mass movements, which and some may block rivers and transport a lot of debris. Next one. Okay, you see here this crest, of course, looks very irregular. It is also at the elevation of about 3,500 meters. So the rock came down from about 5,000 meters there. And it was also a mixture of ice and rock. And in the meantime, I think the dam has settled about 60 or more meters. The next one. It creates a big lake, which is still there. Okay, also in in Tajikistan is still the world's highest rockfill dam. Burek Dam is 300 meters high. Next one is in that region. What we see here is from the upstream phase. Next one. Okay, this is also from, let me say, former Soviet Union. This is in Uri arch dam. It was the highest arch dam until recently with 272 meters. Next one. Okay, and here in India, people talk about the DBAM project. I was also originally involved with NHBC in, I think, 2007, and we have done, let me say, the seismic analysis and design of this gravity dam, and I thought the seismic input was provided by Dr. Gupta at that time. Okay, next one. This very highly seismic area. This is a project which was just completed in Pakistan, in Kashmir. And this dam here, I must say, on the right side, you may see here a small embankment dam. That is a location of a main boundary thrust, one of the main fault zones in the Himalayas. And there was a strong earthquake in 2005, which killed about 80,000 people in that area. So it is an extremely highly seismic area. And I would just like to mention for those who were used to small seismic coefficient, in that project, the horizontal peak ground acceleration was taken as 1.25 G, you know, not 0.1 seismic coefficient. It will, if you would take that as a relation, it would be a factor 12 times more. What you see on the left side, the descender, and of course here the reservoirs are also small. They are silted up. It is this Neelum Valley which comes into India. Okay, it is completed in the meantime. Okay, but I just wanted to show this example that in the Himalayas, in a foothill of the Himalayas, if you are close to faults, the seismic hazard becomes very, very large, as you see here. And the whole design basically was based only on seismic, I must say. Here, this is just this intake structure. Next one. Okay, seismic hazard. Next one. Okay, I always like to say that, and I hope in this course you should be aware that the seismic hazard is a multi-hazard for large dam project, which includes what has been mentioned, ground shaking. Okay, Dr. Gupta has given that, and most earthquake regulations are concerned with this hazard only. And I must say, most engineers are only dealing with that still now. But we have other hazards. Number two is a fault movement in dam foundations, or I must say we have had this case in Iran, or discontinuities in dam foundation near major faults, actually, which can be activated by very strong earthquakes, also causing like it's a secondary fault, you can say. It is they are not seismogenic faults, they are faults which can be, or discontinuities which can be activated by, let me say, a main fault, which is very close to a dam site. So you may have to look into this issue, and in that dam in Iran, this has been the dominant hazard. Some of these faults have shown traces of movements of 8 meters, okay, over maybe a million of years, but they could be reactivated. Number three, we have fault movements in a reservoir. They may create some water waves. Hepken Dam is one case in the United States, which has caused some sages in a reservoir, but it was not caused by the fault movements, but the fault movement gave some non-uniform ground motion, sorry, for non-uniform ground displacement near the reservoir, which then caused, let me say, large vibrations uh, or sloshing effects in a reservoir, which then caused overtopping of a dam crest during a 3-4 incidents. Okay, mass movements are also a problem with access roads. We were, let me say, we visited the Wenchuan earthquake, some dams in the Wenchuan earthquake area, and one important dam was not accessible for about 12 months because of landslides. There were so many landslides. And there are some other site-specific and project-specific hazards. Next one. So you have to look into all these hazards. Next one. Okay, just to say something about PGA value, peak ground acceleration values. Some people are very much concerned about that. And I would like to give this example. It's an extreme example here from an earthquake, Miyagi earthquake in Japan, where people measured near, let me say, near the epicenter. They measured quite large accelerations. You see the red numbers. They show accelerations of over 1G. The maximum here is at 2005 centimeters per second square. That means it is 2G. Okay, more than the one I've mentioned in Pakistan. In the meantime, people have measured peak ground acceleration, I think in Japan, close to an earthquake up to 4G. So what I want to say is even moderate earthquakes here, 5.5 magnitude shock, magnitude 6.2, magnitude 5.3, they may create quite big accelerations. But the peak ground acceleration is only half of the story because the damage processes in dams depend on the duration of strong ground shaking. If you have these shocks, the duration is only maybe 1 to 2 seconds. They do not create big damage. So it is more the long duration, and I'm quite happy to have seen the records from Dr. Gutta. He used also what we also propose, a reasonably long duration of strong ground shaking. It is very important. We make their conservative assumption. Next one. Okay, here's just some measurements from earthquake in Japan, a magnitude, moment magnitude of 8.3. And I would just like to refer to the red one. I cannot point it here. Red one is an example of a 140-meter high gravity dam, which it has been instrumented by an instrument at the base and at the top. I must say, I also recommend you in India, in your big dams, that you should have some seismic instrumentation. But the minimum would be 2. And as you can see here, peak ground acceleration at the foundation is 51 gal, and at the crest it is 677. So it is about a factor of 13. So the dynamic response, if you look the peak ground acceleration from a base to a crest of a dam, is multiplied by a factor of 13. In a pseudostatic, you would have no amplification. It would be also 51. But you have, from the dynamic characteristics and mainly also damping relation of your dam, you may have in some dams very large amplifications, especially when the damping is small. The second case is a green one, is a 120-meter high rockfill dam, also with a peak ground acceleration at the base of 54 gals. Okay, gals is a Japanese unit. It is 1 gal is 1 centimeter per second square. And the crest is 325, so it's an amplification factor of 6. Usually people doing some seismic analysis of embankment dams, they get amplification factors of 1.2, 1.5, maybe 2 is an exception, but for smaller ground shaking, you can still have quite larger amplification effects. Next one, these are actual measurements. Next one. Okay, I would also like to mention, or it was pointed out previously, you had a number of magnitude 8 earthquakes, and it is clear if you have very strong earthquakes, seismicity will remain high, as in the case of this Andaman earthquake of 2004 with a magnitude of 9.1. And you see here 70, 80 days after the earthquake, you basically had every day or every day you had earthquakes with aftershocks with magnitudes between 5 and 6, and the main aftershock was occurring after 60 days with a magnitude of over 8. Next one. So please keep in mind, once you have strong earthquake, the seismicity may remain higher than before for quite some time, some weeks, months, or even years. Next one. Okay, this is an example. You know, in the Andaman Sea, Andaman Island, you also, it belongs to India, you also have a dam, Kalpong Rockfill Dam, and you see here, of course, the loss was mainly due to tsunami, but there was also this dam, and you see here this longitudinal crack along the dam crest on this biggest dam in the Andaman Sea. Next one. Seismic performance of concrete dams. Let me say a few words about that. Next one. Okay, this is a Sefidrut Dam in Iran, which was subjected to 1990 earthquakes. It's already 30 years ago. Magnitude was about 7.4, and the epicentral distance is assumed to be just about 100 meters from the footprint, or let me say, from the downstream face of the dam. Next one. Okay, where some cracks occurred here is at the upstream phase. Cracks mainly occurred here along the lift elevations. You can assume that in concrete dams, I must say, the cracks will not occur just somewhere. It will occur for example, at lift elevations, or next one, or at also elevations where you have sudden changes in the geometry at kinks. Okay, you see here's this crack. This crack is not just a surface crack. This crack penetrates through the whole dam body, 20 meters in the buttresses. Next one. Okay, but besides this, the dam, also you have to take into account, we will have a lot of rock falls. You see, if you have an unprotected transmission line, this is the first transmission line from a power plant from a previous dam, it needs only a small rock, basically to topple here to destroy this transmission tower. It would be easy actually to protect such towers. We do that in Switzerland for avalanches, and you are probably, I think you are also doing it in India. Next one, it is simple to protect that. Okay, you see also here the buildings on the side of that dam. It is mainly used for irrigation, but also for power production. And you see during that earthquake, about 40,000 people were killed close to that dam site, actually. So basically all structures were destroyed. Next one. Which was expected because the buildings are not designed against that high level of earthquakes. Then the dam, as you have seen in a dam, there were just some cracks, but the buildings basically were all destroyed. You see here some equipment. It's a transformer derailed. Next. Next, please. Okay, we see here from the switch yard, we have some overtopping of some insulators, ceramic insulators, and it is basically due to ground movements. Please keep in mind, in a mountainous regions, the switch yard is basically built on excavation with proper foundation, but other parts may be fill material because you do not have a sufficiently flat area, and of course the landfills are very susceptible to earthquake ground shaking. Next one. Okay, we have plenty of rock falls here. You see the dam in the background, so the roads are inaccessible. Next one. So please do not underestimate the rock falls. Okay. It is not always climate change. It is, if you have an earthquake, you really have plenty of rock falls in the Himalayas. You see some of the rock boulders very large. It is just below these big boulders is the intake of the Morning Glory spillway. Fortunately, they didn't fell down there. Next one, but we have this problem. You see also in a power plant, there's a lot of normal structural damage. You see on the left also some sandbags because the Iraqi Air Force have attacked this power plant repeatedly during the Iran war in the 80s. Next one, it was still there. Next one. Okay, the dam was strengthened after that earthquake by a number of rock anchors. Each block had 12 rock anchors with a capacity of 100 meganewtons, 10,000 tons. As you can see here, to strengthen the top where the cracks basically occur. Next one. Okay, you see here this work which was going on. It costed about $25 million at that time in 1990, 1991 when this was done. It was these rock anchors, but there was also some leakage, so there was some epoxy grouting being done, and this is some drilling operation for grouting. Next one. Okay, these anchors were installed. This is just during the installation. It was cut. It was on all the blocks of this buttress dam. Next one. Okay, the famous case is a Koina Dam in India. You know that the Koina Nagar earthquake magnitude 6.3 or 6.5. We like to refer to that in my committee to 6.3. And there was some, let me say, cracks at the location of stress concentration. As you see here, the geometry of this gravity dam is unusual. Of course, it depends, or let me say, the normal gravity dams have just a constant slope, but here it was decided to hasten the dam during construction, creating this weakness at this kink. Okay, after that earthquake, it was strengthened also by rock anchors here, by anchor bars as shown here. Next one. And the dam was strengthened by adding a buttresses. Okay, you see here a buttress was added, and if you look with geometry, it looks now more like a triangular shape, which is a traditional design for gravity dams. So the dam has been strengthened, not only repaired. The dynamic characteristics of this dam have changed. Okay, next one. Okay, faults in dam foundation is also one of the hazards. Next one. Okay, this is also the Sefidrut dam. This is more a crack which has been reactivated because the dam is located on different geological formations on andesite and basalt. And at the interface there was already an old crack in the foundation gallery. And from small movements, this crack was reactivated. And you see here from high water level, the water was splashing along these small cracks in this foundation gallery. Next one. Okay, if there is some major fault movements, you have to assume that concrete structures cannot resist such movements. As you see here in Taiwan from 1999, it destroyed 2 openings of this weir. It didn't, and the reservoir was released. It didn't result in a catastrophic flood downstream because during the monsoon time, all 20 or 22 gates are open, so they will release much more water than by the failure of these 2 gates. But you see, if you have substantial displacement, basically you cannot prove the safety of this dam. And you should not, you shall not, or you must not build dams over concrete dams, concrete structures across faults. Next one. You cannot protect them. Okay, seismic performance of embankment dams. Next one. Okay, this is from a Butch earthquake. A lot of small earthen dams which were damaged. Fortunately, no catastrophic release of water occurred because in January, it's now 20 years ago exactly, the reservoirs were basically empty. Next one. Okay, with some Butch earthquake also. Next one, some cracks. Also Butch earthquake, some larger cracks of some earthen dams. Next one. Okay, some of the cracks are wide. Some people think cracks are very deep. Cracks are not so deep because you know in earth structures, the horizontal stress is about 0.5 times the vertical stress. So the deeper you go, the larger the horizontal stress, which prevents propagation of cracks to greater depth in earth structures. Next one. Okay, some typical cracks. It is Dr. Jain, Sudhir Jain, my old friend. I think now he's director of IIT Gandhinagar. Next one. Okay, liquefaction is a problem, and that is basically the start why I also started my career as an earthquake engineer. Because after that earthquake, I worked in a laboratory of hydraulics, hydrology, and glaciology, the Swiss Federal Institute of Technology. And people were concerned about the earthquake safety of dams, and at that time people still thought that by early warning you could protect the people, but this was, let me say, was a too optimistic assumption, of course. You see here, hydraulic fill dam, this time, the earthquake has just occurred, the anniversary was just 50 years ago, it's on 9th of February. Okay, you see here, due to liquefaction, we have very large displacements of about 60, 70 meters of this embankment dams. Next one is a hydraulic fill dam. Next one, okay, you see here another photo of this dam when the reservoir was slightly lowered. Next one. So this basically is a start. I must say this earthquake I like to show because it is basically the start of modern earthquake engineering in dam engineering. And I must say since 1971, people basically know that that dams, sorry, that the pseudostatic method is not suitable for, let me say, to check the seismic safety of dams. It's not something new. It is very old. It is already 50 years old. People doing structural analysis, of course, they knew it even earlier. But this earthquake has shown that these methods are obsolete, and based on that experience, I must say the development has been going on, and this pseudostatic method has been replaced, but also it is still being used in some places, as it was mentioned, India, China, South Korea, and so on. It should not be used in highly seismic areas. This is from Kobe earthquake, which shows you that in the upstream phase, you actually have a slope failure, like the slopes you assume if you do dynamic stability analysis. Next one. I must say I have to speed up. Observed earthquake performance of fill dams. Modern well-built embankment dams have performed well. Compacted clay dams have performed well. Rock fill and concrete face rock fill dams have performed well. The dams which have shown problems are insufficiently compacted sand or silt dams, and mainly tailing dams, and what I've shown before from the San Fernando earthquake, the hydraulic fill dams. Okay, these are the dams which behaved very poorly under strong earthquakes. Next one. Okay, now seismic design criteria for large dams. Next one. Okay, basically the safety criteria are as follows. I must say this is relatively new, or please keep in mind. These general safety criteria are the following. Number one, to retain the reservoir is what people always have done and are doing now. And to protect, I must say the objective is, it was also mentioned at the very beginning, of course, to protect the communities downstream from a catastrophic release of water. Okay, this is always the case. But number two, which people have not really looked at, we must be able to control the reservoir after an earthquake. Because I must say, if your let me say spillway or low level outlets are out of order and the power plant, for example, is shut down, you cannot release any water. So if you cannot release any water from your reservoir after the earthquake, depending on how full the reservoir was and what is the inflow, it may overtop days or weeks after the earthquake. Okay, people have not really realized that. Therefore, today, the seismic design criteria are that low-level outlets and spillways, if they are gated spillways, they must withstand the same earthquake as a dam body, and they must still be functioning, which is even strict, very strict. And number three, it should be possible to lower the reservoir level after an earthquake, if your dam has been damaged, of course, it's easier to do the repair work in the air. Or secondly, we may ask for lowering the reservoir if we want to increase the safety of a damaged dam, or when there are doubts from politicians and some local community people about the safety of a dam. So what you can do on the short term to increase the safety of a dam is to lower the reservoir. And for that, it is very essential to have low level outlets. So I would strongly recommend you in India to also have low level outlets if you do not have. Next one. Next. Okay, just to give a quick overview on the Icold seismic design criteria for large dams, we have to consider, let me say, different elements. Number one, if you look at dam body and safety critical elements, that are the spillway and low level outlets, we consider two levels of earthquakes. Number one, the operating basis earthquake, which has a return period of 145 years. This is what we propose. Some people like to use longer return periods. It's not forbidden. Okay, but 145 years we think is reasonable. The second earthquake is a safety evaluation earthquake. If we do it in a probabilistic way for large storage dams, we propose to use a return period, recurrence periods of that earthquake of 10,000 years. And of course, we also propose to use in a deterministic analysis the worst case earthquake scenario, I must say the methods which were presented by Dr. Gupta. Also for the appurtenant structures that are powerhouse, desander, power tunnels, penstock, switchyard, transmission lines, and so on. If you do not have any specific codes in your countries, you should at least use the building code. Okay, the requirements of a building code, which in most countries is based on a return period of 475 years. Okay, and finally, we also have some temporary structures. You know that in India, it may take quite a long time until you complete the project. So also some temporary structures and also critical construction stages have to be checked for some type of earthquake. Next one. So that is what is the current Icold guideline. Now, if you look into safety critical elements, we look into, and I would like to mention it explicitly, spillway gates. And if we talk about spillway gates, it means the gate system, including motors, oil hydraulic systems, power supply, control units, emergency power supply, and so on. Okay. Secondly, we have safety critical elements are also gates and valves of low level outlets. Sometimes these are called bottom outlets, irrigation outlets, sediment flushing outlets, and so on, and also their operational systems. Okay, now please note that the safety critical elements are used to control and lower the reservoir after strong earthquakes. Therefore, the same seismic design and safety criteria apply for the safety critical structures as for the dam body. The hydromechanical engineers, electromechanical engineers who are involved here, they have not yet realized that. This is a new. Next one. Okay, where shall we apply the different design criteria, OBE and SE? I mentioned already up to now, everybody has been doing it for the dam body. And if you look into the dam body, several dams have also saddle dams. Please keep in mind that the same criteria apply not only to the main dam, they apply also to saddle dams if a reservoir could be released. Okay. Number two, it has to be applied with concept of two levels of earthquakes, has to be applied to safety critical elements that are the spillways and low level outlets, I mentioned just before, but it also has to be applied to dam abutments, number 3, because the abutment stability is basically a main concern for arch dams. Okay, we are having been involved in some big arch dams in Iran, and there I must say the abutment stability is a main issue. If the abutment stability for the safety evaluation earthquake is not okay, of course, then the dam safety is also not okay. And also number 4, we have to look in the reservoir slopes, because rock slides or landslides may block intakes of critical safety elements, or may damage them, or may create important impulse waves in the reservoir. I've written this here before the Chamoli incident. So based on the Chamoli, I would say you would even have to look into slope in a catchment area, which can transport big debris and amounts of flood water into a reservoir. Next one. Okay. Now, what are the good news on the earthquake safety of dams? Water storage dams, I would say embankment dams, only one dam failure with loss of lives worldwide up to now during the 2011 Tohoku earthquake, also 10 years ago, where 8 people were killed in a flood wave released by this reservoir. For concrete dams, no concrete dam has failed which has caused loss of lives up to now. This is good news. Secondly, tailings dams. Several tailings dams have failed during strong earthquakes in Chile, which caused loss of lives. The tailings dams are problems. They are basically a problem because those mining company, their core business or core competences is not in dam engineering, so they think it's a nuisance to have these tailings dams. So sometimes you may get the impression that some of these tailings dams are really not safe, otherwise they would not have failed like in Brazil in recent years, also in Australia. Okay, note please the excellent seismic performance of water storage dams shows that the seismic safety concepts in use have been very successful. It does not mean that these dams are over-designed and the seismic safety standards can be lowered, as some people may conclude. So please, the good performance, you should not congratulate yourself and say you can lower your safety standards. It would be a wrong approach. Usually it goes in the opposite direction. Next one. Okay, I still have 10 minutes. I can skip that. The main steps for seismic safety evaluation of existing dams. It consists of the same one. Of course, the first, what Dr. Gupta has shown, determination of the seismic failure modes of the dam and estimating of the ground of the ground shaking acid. So that is basically the input. The other steps are the same, like for the seismic design of dams. Next one. Okay, this is for fill dams. Next one. Okay, for concrete dams is the same. I must say for fill dams, I would like to say the basic failure scenarios for fill dams are overtopping, because overtopping leads to progressive erosion, and also it is internal erosion. It also leads to progressive failure of a dam. So you have to prevent these two failure modes for embankment dams. For concrete dams, it is basically the dynamic stability of the dams, and it is also the dynamic stability of the top portion of the dam, basically. Next one. Okay, I mentioned already tailings dams I must say what I, as a water storage dam expert, we strongly recommend that the same seismic design criteria should apply as for water storage dams. And it is even for tailings dams, as they are converted, they stay there forever. There are even higher seismic standards required. Because unlike a water storage dam, they will stay much longer. Next one. Seismic rehabilitation. This is the last part of existing dams. Next one. Okay, evaluations have been done in California already 20 years ago. 1,200 dams have been checked there, and it was found that about 10%, 116 dams, about 10% had some kind of deficiency, seismic deficiency, and some of the measures taken are listed here. And I must say, of course, if you find out that the dam is not seismically safe, what can you do? You can lower the reservoir. So by temporary storage restrictions, you can increase the safety of your reservoir. But of course, the dam owners do not like that, so they invest in strengthening. So there are different measures which are required. We have done a similar check just about 5 years ago in Switzerland for 200 dams, and it has shown that basically dams which have shown already other types of problems also have seismic safety problems. Next one. So we recommend you in India and also in other countries actually to look into the seismic safety of your existing dams. And it is most likely that a couple of them have inadequate safety, as in the case of California, which is already a region of very high seismicity. Now, this is an example of seismic rehabilitation of a dam in New Zealand. It's also a highly seismic area with arrow. It shows here a spillway. I say the spillway must be safe for the same earthquake as the dam body. So this spillway here, it was designed in the 1950s with a pseudostatic method with 0.1 seismic coefficient of 0.1. And you see on the right, there is also an embankment dam. Next one. Now, a seismic reassessment has shown the original design a seismic coefficient of 0.1, which corresponds to an equivalent acceleration of 0.1 g. And the rehabilitation has shown, because this lifting structure, is on a crest, and I've shown before, on a crest you can have large dynamic amplification effects. And also the seismic hazard with a modern method, you get much higher hazard. So therefore, if you take that into account, for the rehabilitation, they arrived at 1.8 G. Using a pseudostatic method, you get only 0.1. It is 20 times larger if you do a dynamic method. So therefore, if you do a seismic safety check only on the pseudostatic method, you greatly underestimate the seismic safety. It's basically unsafe, as it has shown in this case. And you see here, after strengthening, it had to do, very significant strengthening had to be done, and the structure looks very different. Next one. So the pseudostatic method can give completely wrong results for some structures. So you cannot trust on that. Next one. Okay, this is an extreme example, I should say. Next one. Okay, we see here a multiple arch dam. Basically, the strengthening which has been done is a shear resistance of the abutment, where some RCC has been placed to increase the shear resistance. Next one, sliding resistance. Okay, for embankment dams, you can do a multiple strengthening. You can put berms upstream. You can widen your crest. You can heighten the dam. You can add some berm in the downstream part, adding some filters. Next one. Okay, you see here, this is a rehabilitated dam, also in California here using the methods which I've shown in the previous slide. Next one. Okay, I mentioned here just very briefly structural safety, and if you talk about seismic safety assessment of existing dams, if you talk about safety, please keep in mind that for dams with a large damage potential, we use a sophisticated a safety concept. Today we have to use that, and which includes the following aspect: structural safety, and in this case earthquake safety, and I've discussed now only earthquake safety, but it includes also dam safety monitoring, it includes operational safety and maintenance, it includes the guidelines for reservoir operation after earthquakes, for example, and it also includes emergency planning, and it includes water alarm systems, evacuation plans, engineering backup, and so on. So we have to take that into account as well. Also in my presentation, I have discussed mainly structural safety aspects. Next one. Okay, for the analysis, those who want to do analysis, for the OBE, we expect that for concrete dams, we do not have large stresses, so we can do a linear elastic dynamic analysis, which shows here an arch dam with the interaction of the reservoir and the foundation. Next one is a quite demanding analysis, but for the safety evaluation earthquake, you can do actually simpler methods, which shows here a case in Switzerland where we had already a crack in a dam due to alkali aggregate reaction. So the question is this dam still safe? And you see if it is a cracked dam, if a dam is cracked, basically all deformations occur in this crack. And this shows a rocking and sliding of this dam, and at the end of the earthquake, as you can see, at the right, we have a displacement of 70 centimeters, which is considered as okay for the safety evaluation earthquake, which may occur never. Next one. So the dynamic analysis for let me say for a safety evaluation earthquake or a nonlinear analysis could be actually much simpler, or there are models like shown here, could be much simpler than those used for the linear elastic dynamic analysis. Now for the instrumentation, also to say quickly, I recommend you to have seismic instrumentation. The minimum is an instrument on the crest, and at the bottom, here is an example of Inguri, which has more instruments. Next one. Okay, here are some instruments. Next one. Need some power supply. Okay, next. Next, please. Okay, emergency action planning is also important. Next one. Okay, just to show you some examples, some people have presented some dam breach flood wave analysis, and of course a strong earthquake may be a trigger of a dam failure. You do a dam breach flood wave analysis, you determine the maximum flood wave level, and that is the level of the energy line, I must say, and based on that you can draft some evacuation plans, and we have some alarm system with some sirens. Next one. So you should have that. Now to come to the conclusions. Number one, please keep in mind the seismic hazard is a multi-hazard for most large dam projects. Ground shaking is the main hazard considered in all earthquake guidelines. The other seismic hazards, such as mass movements, may have been overlooked, like in Chamoli now, which has shown. But it is not just there. We have observed that in several cases. Now, number two, the very popular pseudostatic analysis method and the use of seismic coefficients to represent the earthquake ground motion are outdated concepts and shall no longer be used for large dam projects. The results of pseudostatic analysis may be wrong. These facts have been known since the 1971 San Fernando earthquake. It's not something new, it's something very old, but people adhere to a pseudostatic method because it is so simple. And maybe some people don't have a proper budget for doing a proper analysis. Number three, the characterization of a seismic hazard by a seismic coefficient, I would say, is voodoo science, is not based on scientific principles. So, but still people try to justify it again because it is so simple. Next one. Number four, for the dynamic slope stability analysis, I must say, or Dr. Gupta has shown, in India, apparently it is allowed to mobilize some of the cohesion, but we think you should only take into account the friction resistance, because once you have a small movement, actually only the friction resistance are available. So you should only use the residual strength properties, I must say. Number five, we can say dams are not inherently safe against earthquakes. Good design and high quality construction works are prerequisites for good seismic performance. This is very clear. Now we can also say technology for building dams that can safely resist strong ground shaking is available. We must make use of it. Number seven, emergency planning and the installation of water alarm systems in a downstream region of large dams, we think is a must. It is also in that connection, it is important that we have low-level outlets in our dams. If that, I would strongly recommend that. We have done that in Switzerland and we have had good experience. And number eight, okay, that is what I have said already. So thank you very much, and I think I have taken about 1 hour and something which was allocated to my presentations. So thank you very much. You can close this presentation. We can go to the next, I understand. Okay, this just my address. I should say I'm in Zurich. Now it is 10 to 8 in the morning. I do not know who is chairing this session, so I would assume that you should upload the next speaker.
My name is Ravi Bhandari, and I work in a company. Today I am going to present on dam, the higher. These are the presentation outline of my presentation. Nepal has more than 6,000 high gradient rivers, which shows that the high potential for hydropower development. But
We do not see your presentation.
of dam in higher Himalayas is challenging due to its complex topography, unpredictable geology, and high seismicity. One of the projects, Betan Karnali hydroelectric project, studied by an engineering company, lies near the MBT. And the other two projects, Pukot Karnali hydroelectric project and
May I disturb you quick? We do not see your presentation. I do not see your presentation.
Yes, sir. Anything problem?
Hello, could you upload once again?
We don't see the presentation. I don't see the presentation.
Okay, you are not able to see.
Yes.
And Ravi sir, you?
Yeah, I'm saying, yeah. No problem with
Okay.
me.
Yeah, it's okay. It's okay. Martin, this is the problem with your WebEx only. So please, we are moving ahead.
So not able to see presentation.
And Rizwan sir, you also can't see.
No, no, I am not also able to see.
Okay, let me check. Now it's visible, sir.
Yes, it is visible now.
Okay.
Okay, now.
Are located near the MCT. Now I'm going to talk about the Pukot Karnali hydroelectric project dam. The proposed dam is 160 meter high as gravity. The foundation bedrock is about 55 meter below the existing river level, which is major challenge of this project. These are the plans and section of the proposed Pukot hydroelectric project dam. Before starting finite element analysis of the dam, stability analysis is performed to obtain an initial section of the dam. The dam stability analysis is performed based on USCC guidelines. After a stability analysis, finite element analysis is performed to check the response of dam more details. Elements of the dam and the foundation are modeled as 2D plane strain element. Foundation is modeled as massless. Height of the tallest section is 160 meters from the riverbed, from the bedrock, and base width is 150 meters. The material properties assigned during final element are as shown. The site-specific hazard analysis is performed and response spectrum are prepared for different region periods. 5 sets of response spectrum math, acceleration time history records are used to evaluate the seismic response of the dam. Both horizontal and vertical acceleration time histories are assigned in finite element model. Hydrodynamic load is assigned as Westergaard mass. The linear response of the dam is evaluated based on envelopes of maximum stresses, time history of maximum stresses, and time history of maximum stress. Plot of the particle stresses contour shows that the stress is concentrated at the heel of the dam and at the slope change location at the upstream face of the dam. Among the 5 sets of earthquake record, time history to record gave maximum top displacement of 236 millimeters. Acceptance criteria of the linear time take based on USCC. The guidelines suggest to measure acceptance criteria, which are plot of overstress area versus demand to capacity ratio and plot of cumulative inelastic duration versus demand to capacity ratio. Results show that the response of the dam is slightly higher than the acceptance criteria for elastic range. Cracking will be started at heel of the dam, which can be best assessed by performing nonlinear time analysis. Next important result obtained from linear time history analysis is plot of instantaneous sliding factor safety. Results show that sliding factor safety rarely fall below 1, which ensures that the dam is safe sliding. In conclusion, linear elastic time history analysis indicated that the dam suffered cracking at limited area of heel, and nonlinear time history analysis will be necessary for a better estimate of this. And results showed that the instantaneous sliding factor of safety rarely fall below 1, indicate safe sliding. Thank you for your attention.
I thought we will go with the next one and to have questions at the end.
Yeah, Rizwan sir, can you come on, please?
Okay, I will present. Okay.
Yeah, my screen is visible, sir?
Yeah, visible. Yeah.
Yeah. Okay. So when you need to change the slide, please say next slide.
Okay, okay.
Okay, sir. Mic is yours.
Okay. Good afternoon. I will be presenting one case study on 3D stress analysis of edging dam by finite element method towards strengthening. It is a case study of Icold Dam. So before going to case study, I will give some background and causes of dam failure and some methodology about this stress analysis. Next slide. Next slide. So nearly 200 major dams in India are more than 100 years old. The first hydroelectric power dam in the world was built in Appleton, Wisconsin in 1882. In India, Tata built first hydroelectric power dam in Western Ghats of Maharashtra in early 1900 by constructing Tokarwadi, Suravata, Valvan and Mulsi dams. So you are seeing a view of this Tokarwadi dam, and the oldest dam is Kalani Dam. That is Grand Anicut near Trichy. Next slide. Majority of the hydroelectric projects in India have been constructed post-independence based on conventional design approach without much consideration of earthquake forces. At present, India ranks third globally, having 5264 large dams and 437 dams under construction.
Yeah, Rijwan sir, sorry for interruption. Can you open your camera?
Okay.
Yeah.
Yeah. Okay. So almost
Thank you, sir.
almost 40% dams lie in Maharashtra. Though India experiences least earthquake in the world, but due to extensive damage in Koyna Dam during earthquake, has raised concern about the structural safety of dams in India. At present, most of the major dams in India are more than 40 years old, which have either been designed without consideration of earthquake forces or very small effect has been considered, which resulted in under design as per latest design criteria mentioned in IS 1893 2016. Next. Dam failure results in a catastrophic breach break followed by a flood wave, often with considerable loss of life and property. Safety during design, construction, operation, maintenance, and surveillance of dam is a must. Next. Main causes of gravity dam failure: lack of shear strength and discontinuity in foundation, excessive uplift in a foundation, inadequate or non-existent drainage system, lack of dam stability, excessive or differential deformation of the foundation, piping and erosion in the foundation caused by high permeability, flaw in the design, lack of supervision during construction, no monitoring or warning systems were out of order. Next. Human error during site investigation, design, construction and operation, inadequate foundation investigation, incomplete data on available material, incomplete first impoundment, frequent strong earthquakes, decay due to aging effects, incorrect operation of floodgates, insufficient monitoring and data analysis, lack of preventive measures or repair work, accidental damage may create apprehensions about the safety of the structure, like in Uttarakhand. Next. Symptoms of distresses in the dams are observed in the form of cracking, spalling, concrete disintegration, seepage. Next. So cracking generally takes place at two stages, that is before hardening due to shrinkage, setting shrinkage, drying shrinkage, settlement shrinkage and construction flaws, and after hardening it is due to physical causes, chemical action, alkali aggregate reaction, thermal conditions and stress concentrations. Here you can see the various types of cracks. Next. Spalling is the loss of larger pieces of concrete or flakes due to high stress in the concrete, like in figure 1. Then disintegration, deterioration into small fragments and individual aggregates, scaling, local flaking or peeling of surface mortar caused by hydraulic pressure, freeze cycles affecting the concrete at the surface, honeycombing exposing coarse aggregate due to poor compaction and excessive seepage through the dam body. Next. These consequences are as follows. It will result heavy leakage or seepage, then development of cracking, large displacements, heavy leaching of cementitious material. Due to aging, safety issues of water conductor system also get affected, raising apprehensions about the structural safety of the dams. Next. These are the some photographs showing the heavy leakage through the dam body in Masonry Dam. Next. These are the extensive damages in Koyna Dam during the earthquake of December 11, 1967. Here you can see the cracks along the length of the dam, and this is strengthening in progress. Next. This is the extensive cracking took place in Hirakud Dam due to alkali aggregate reaction. Entire this foundation gallery longitudinal cracks are there. Then foundation gallery also longitudinal cracks are there, and a lot of damage is taking place in the under sluices. Next. There was sudden discharge in Bandadara Dam due to internal cracking. So this dam was strengthening. Again, this structural safety audit is going on. This is also Masonry Dam. Next. This is the common feature on most of the old dams, in Masonry dams particularly. A lot of leaching of cementitious mortar is taking place in downstream phases, foundation gallery as well as in inspection galleries, raising apprehensions about the safety of these dams. Next. So requirement of safety review of the dams. Frequent storm earthquakes decay due to aging effects and accidental damage may create apprehensions about the safety of the dam and necessitate rehabilitations and strengthening of the existing dams. Stability of stress analysis of the dams is much more complicated and involved than other structures on earth. Interaction between dam and the foundation rock and hydrodynamic forces need to be modified in a realistic way. The methods of analysis need to be applied suitably to get correct estimation of the response, as the results are very sensitive to the approximations and idealizations made. Dynamic results need to be calibrated by monitoring the response to actual earthquakes and forced vibration tests. Next. Earlier practices of analysis were conventional theoretical methods based on experiences or experimental techniques like photoelasticity, stress bands, physical model studies using strain gauges, matrices method of analysis. Now the method of mathematical modeling using finite difference method and finite element method. These old dams like this Hirakud Dam and this Bhakra Dam, most of the dams have been studied by photoelastic technique as CWPRS. Next. Methodology for reviewing structural safety of the dams. So, physical inspection of the dam, assessment of weak dams in the body of the dam by seismic tomography, in situ determination of properties of the dam material by nuclear and sonic logging, identification of seepage routes by tracer technique, laboratory determining properties of the dam material, in situ determination of the material properties by flagjack test, estimation of site-specific seismic parameters, stability analysis of the dam by FEM under static and earthquake loads, improving structural safety through repair and strengthening. Most of the challenge for old dams is to estimate the in situ material properties. For concrete dams, you can take the course. For masonry dams, it is a big challenge to assess the properties. So, indirect methods are utilized to know the properties of the masonry. Next. So types of structural stability analysis of dams are conventional analysis, that is vertical cantilever beam analysis, 2D, 3D static analysis by FEM, 2D, 3D pseudostatic analysis using FEM, 2D oblique 3D pseudodynamic analysis using FEM. Next. So these are the some software packages available in the market. ANSYS, Lucis, Solvia, Adina, Nesten, Idea, Ceph, Abacus, Hyperverse, EHD84. So we are having Lucis, Solvia and Abacus softwares as well as EHD84 also. Next. So these softwares have these types of boundaries. That is, we can give free boundaries. The displacements are free in 3 directions, as well as moments are free. Then we can fix. Then we can give the stiffnesses also. That is, we can apply stiffness, spring stiffness also. Next. So these are the various material models available in the softwares. Generally, we carry out elastic analysis. Sometimes we have to carry out this orthotropic analysis, where this foundation, where the foundation is layered foundation is there, so where this E value is not same in all the directions. Next. Next. This already discussed. Next. Yes. So after this, then allowable stresses is also big issue in this dams. So as per 6512/1984, the tensile stress in concrete gravity dams under simplified approach is taken as 4% maximum of the characteristic cube compressive strength. Pardon me. As per latest design practice in India, the tensile stress using modern rigorous methods of analysis under static and so dynamic conditions is taken 1/8 to 1/10 of the characteristic cube compressive strength by CDO practices. As per international practices, the spirit tensile test or modulus of rupture test used to determine the tensile strength. For initial design investigation, static, pseudostatic, pseudodynamic, and linear dynamic analysis, permissive tensile strength of concrete calculated by Raphael's approach, that is direct static tensile strength is FST is 1.7 FCK power 2/3. It is in PSI. Next. Similarly, for static tensile strength determined by spirit tensile test increased by 1.33 to be comparable to the standard modulus of rupture test. It is modulus of rupture. It is flexure tensile strength is find out as 1.33 of direct tensile strength, which comes out 2.3 FCK power 2/3. Dynamic tensile strength of concrete calculated by increasing 50% of static tensile strength is comes out to be 2.6 FCK power 2/3. Next. So this is the acceptance criteria for gravity dams. It has been mentioned in the latest draft IS code as well as engineering monographs also. So demand capacity ratio DCR is computed as a ratio of stress demands to the static tensile strength of the concrete. If DCR is less than or equal to 1, then no damage is seen in the dam and dam is considered as a safe. If DCR is greater than 1, then damage will take place. Damage is considered acceptable if DCR is less than 2 and the limited area to damage is less than 50% of the cross-sectional surface area and cumulative duration of the stress exertion beyond the tensile strength of the concrete falls below the performance curve. So this is very important graph. Next. So few important projects studied at CWPRS. We have carried out 2D dynamic 2D stress analysis of this Srisailam Dam, Kranja Super Dam, Indrasagar Dam, Omkareshwar Dam, Sankos Dam in Bhutan, Sardar Sarovar Dam also. 3-dimensional analysis of few blocks we have carried out for this Tokarwar Dam. Then 6 blocks of Gurdeswar Weir, Dharwar Dam, entire dam. Then Tilangari Dam, Polavaram recently constructed. Then Hirakud also and Messenger Dam also. Next. So these are the few mathematical models of the studies conducted at CWPRS. Next. Again, it is for Gurdeswar Weir. Next. This is also for Tilangari Dam. Here problem was of uneven foundation. So we have reproduced this typical block with one bay area. Next. This is another block of Gurdeswar where it was having shear zones, weak zones in the foundation. We have reproduced those weak zones in the foundation and then we have analyzed this as a 3D problem by dynamic approach. Next. So types of problem encountered in FEM generally: 2D plane strain problem, is common where this earlier dams were constructed without any joints. So we carry out this 2D plane strain problem like this long walls, monolithic dams. Then 2D plane stress problem, that is we can simplify spillway problems through 2D plane stress problem. Sorry, and jointed blocks of the dam. 3D solid problems, that is more common because dams are having openings also, so many openings, so we can reproduce any type of openings. So generally we carry out 3D solid problem, that is spillway blocks, isolate blocks of the dam. Then shell type of problem, that is penstock type of problems. Then plate, beam. Next. So this is the stability criteria mentioned in the IS code 6512/1984. That is, dam should be safe against overturning at any horizontal plane within the structure at the base or at any plane below the base. It should be safe against sliding or any horizontal or nearly horizontal plane within the structure at the base of any rock seam in the foundation. That the allowable unit stresses in the concrete or in the foundation material should not be exceeded. Next. So this is the equation how we compute this in FEM. So F is equal to W minus into tan phi upon F5 plus CA upon FC divided by P. Here this W minus U is the net downward force. That is, W is the self weight of the dam, U is the uplift pressure, and this C is the cohesion at the interface, and P is the destabilizing force, that is hydrostatic pressure and other horizontal forces, that is inertia forces in case of earthquake analysis we are doing. So this equation can be simplified in terms of stress if we divide this equation by area of contact. This comes as F is equal to sigma zz tan phi divided by F5 plus C upon Fc divided by sigma yz. That is, sigma zz is the vertical downward vertical stress, and sigma yz is the shear stress at the contact. Next. So these are the loads generally acting at the dam, that is hydrostatic pressure, uplift pressure, silt load, gate thrust, dead weight of the gate bridge, gate hosting arrangements, internal pressure inside the sluices, cell weight of the dam, hydrodynamic forces due to water inertia, inertia forces due to self weight of the dam, inertia forces due to silt, and many more forces. Next. These are the 7 load combinations as per IS 6512/1984. Next. So we carry out under these 7 load combinations construction, normal operating condition, flood discharge condition, then flood discharge with extreme uplift, and these 3 dynamic load combinations, that is empty with earthquake, normal operating with earthquake, and normal operating with earthquake with extreme uplift pressure. Next. This is one case study of Hirakud Dam. This problem was referred to us because there are problems of this concrete dislodging at the well mouth entry of the under sluices, because this concrete has become weak due to alkali aggregate reaction. So this problem was first referred as a hydraulic problem, but nothing can be done to modify the spillway at this stage. So this problem was again studied structure problem. So we have to identify the main reason of why the concrete is dislodging at the bell mouth entry, and because in 1990, 30 years back, they have repaired this under sluices by removing those concrete and using epoxy mortar and concrete. But again, this dislodging has started, and a very large amount of concrete are dislodging at the well mouth entry. So this problem was referred to us. Next. So this is the salient features of the Hirakud Dam. Hirakud Dam is a composite dam constructed in 1957-58 in near to Sambalpur at Mahanadi River. Length of the dam including dikes is 25.46 km. Maximum height of the spillway is 60.96 meter. Purpose is irrigation, hydropower, and flood control. This lies in seismic zone 3. So spillway has 2 under sluices. Each block is having 2 under sluices. Total under sluices are around 64. It has two spillways. So objective was to check the stability of the spillway block under static and earthquake forces conforming to IS 6512-1984 and IS 1893 Part 1 2002 as well as 1893. Next. So here the main challenge was to determine the in situ material properties. So for that we have tried various techniques, but most of the techniques were very difficult to apply at the dam because the reservoir is always filled. So we have decided that we will take course from the typical block which has the maximum alkali gate reaction where leaching is more and this cracking is more. So we have selected two blocks, one is left spillway and another is right spillway, and we have finalized the location between the two sluices in the operation gallery, and then we have extracted the core of 15 centimeter to 30 centimeter, 15 centimeter dia to 30 centimeter length from two locations and up to the foundation gallery. So there was challenge because during extraction of the cores, water jets were emerging in the distress block. So then they have put the emergency gate, and this both the sluices were covered with the emergency gate, and the sluice was made empty. Then this cores were extracted, and then again then backfilled with the concrete. Next slide. So these are the extracted cores. So we have done capping of these cores, and then we have tested to determine the Poisson ratio, E value, strength as well as density of the mass concrete at different elevations as per this course recovered. Next. So these are the input parameters used based on this course. So here this dam top, this E values around 3.2 10 to the power 9 kg per square meter. It was varying between 3.1 to 3.2. Poisson ratio is 0.18, and density also varying from 2298 to around 2324, and modulus of plasticity of the dam material is 3.3 10 to the power 9 kg per cm square. That is foundation, sorry, and Poisson for foundation taken 0.22. Next. Then other parameters were taken based on this IS code, that is density of water, and then silt density in horizontal silt density in suspension as 1360 kg per cubic meter. Then vertical density of silt in suspension as 1925, and the seismic coefficients were estimated based on IS code 1893/2016 part 2 by taking the ratio of importance factor and this response reduction factor as a 1. So we have got around 0.24 horizontal seismic coefficient and half in vertical and half in longitudinal. We have taken 0.12 and 0.12. Next. So this is the model, including foundation. We have reproduced around foundation block. We have taken as more than 2 times height of the dam. We have reproduced all the openings, that is foundation gallery, operation gallery, as well as 2 sluices in this, and this spillway, piers, all these things. So we have carried this idealization as a 17,000 nodes and 80,709 loaded linear tetrahedral elements, solid elements. Deflection has been assumed as 0 at the base of the foundation, and along all these sides we have allowed settlement. Here, because elements we have selected because of these so many openings were there, so it was very difficult to give the solid brick elements. Next. So this is the closer view of this spillway block. Here material is taken as isotropic, elastic and homogeneous. We have taken as a 3D problem. Next. So these are the various loads acting in the dam under this earthquake load combination E. Next. So results have been obtained in the form of direct stress, that is horizontal stress, vertical stress, and then longitudinal stress, then this shear stress is also in the form of principal stress, minimum principal stress, and deflection in 3 directions. And then we have plotted the contour surfaces of all the stresses of and displacement along 3 directions. Next. Next. So this is the maximum horizontal displacement variation. Here the displacement is maximum at the top of the dam. You can see under empty conditions, the dam is going towards the upstream side, and in all other conditions, it is going towards the downstream side. Deflection is around less than 3 mm under all load combinations. Next. This is the vertical settlement. Vertical settlement is also less than 3 mm. Next. This is longitudinal displacement. It is also less than 3 mm. Next. This is a deformed shape of the dam. Combination C and E. Here. Next. These are the distribution of the maximum principal stress tension. Here you can see very high tension is coming around the openings of the bell mouth entry under this normal operating condition load B, as well as the normal operating condition with earthquake also. So the area tension is very large. Next. So this is a variation of the maximum principal stress. Maximum principal stress, you can see it is going up to around 16 kg per cm square under earthquake load combinations. Next. This is the distribution of the minimum principal stress compression. At the downstream face, you can see the compression. Next. So compression is not much. It is less than 30 kg per cm square. Next. So these are the results. You can see this is coming around 15.2 kg per cm square under earthquake load combinations tension, and displacement is around maximum displacement is around 2.81 mm. Horizontal, vertical is also less, and longitudinal is also less. Next. Findings of the study: the structural safety of old major dams should be assessed using in situ material properties and site-specific parameters for modern practices such as FEM. From the analysis, it has been observed that maximum principal tensile stress varies from 10⁴ to 15.2 10⁴ kg per square meter under different load combinations. Maximum tensile stress occurs near the hill portion and bell mouth entry of the spillway blocks. Very large volume of the blocks comes under tension during earthquake load combinations as well as static normal operating conditions. Though the mass concrete inside dam body is having very high strength as indicated by the core test results, but surface concrete near to bell mouth entry might have become weak due to aging and acidic water effect, resulting in dislodging of concrete near to the bell mouth entry at some places, because there is a paper mill upstream of Hirakud Dam. So due to this, water is acidic in nature, so it is causing acid effect also on the concrete, which is decaying the concrete. Minimum compressive stress of the order of 29.2 10⁴ kg per square meter under normal operating conditions has been observed to develop in the toe region of the spillway blocks. Minimum compressive remains well within the acceptable limits. The displacements in all 3 directions are not excessive and indicate elastic behavior of the dam. Next. So remedial measures suggested by CWPRS are loose and weak concrete near the bell mouth entry should be chipped out and be repaired using micro concrete, epoxy concrete, and mortar after assessing suitability of these materials under dry as well as saturated conditions. Acid resistant coating should be provided on finished surface of the entire under sluice barrel on all 4 spillway in all spillway blocks. Next. So initiative being taken under DRIP, Government of India is implementing world-funded dam rehabilitation and improvement project in 3 phases. Under DRIP phase 1, nearly 200 dams are being rehabilitated in 7 Indian states, namely Karnataka and this thing with the outlay of 3466 crore. Under DRIP, more than 730 dams have been identified for rehabilitation under these states as well as 2 agencies, that is CWC and Bhakra Gas Management. And Hirakud Dam is also under the DRIP, so this repair work has to be taken shortly. Under DRIP, all major dams under Delhi 53 dams will be evaluated for rehabilitation. DRIP phase 2 and 3 are proposed to be completed in next 10 years. Next. So concluding remarks, all new projects may be constructed new projects may not be constructed in future due to dense population and cost involved, and old projects should be rehabilitated to enhance functioning life of the project. The review of structural safety of old and distressed hydraulic structures should be carried out before taking strengthening measures. And site-specific seismic parameters should be used for analysis to get real scenario. State-of-the-art methodologies such as seismic tomography, nuclear logging, tracer technique, and institute project tests are very useful in assessing the health of the dam. Detailed analysis using FM should be carried out by following BS guidelines. Dams lying in seismic zone 4 and 5 should be assessed under dynamic loading conditions. Next. Thank you for your kind attention.
So I think this was the last presentation for this workshop. Am I audible, please?
Yes, sir.
So this was the last presentation. I hope that participants would have enjoyed the proceedings. We are thankful. Icold is thankful to the speakers for this session for sharing their experiences and making presentation in this workshop. So with these words, we will close the session.
Okay, thank you, sir.
Thank you.
Okay, thank you.
Thank you, Martin.
Okay, thanks, Sunil. Yes.
We apologize. There was a little glitch in the beginning, but finally you were able to log in successfully and make the presentation.
Yeah, I'm also happy about that. Otherwise, it would be annoying.
Yes. Yes, sir. Yes, sir. Anyhow,
Okay.
right. Thank you very much for all your efforts, sir. Thank you.
Okay, welcome.
Thank you. Thank you, Dr. Gupta. Hello.
Thank you, sir. Thank you.
Thank you, Dr. Gupta, for accepting our request at the last minute.
Thank you.
Thank you. Thank you very much, sir.
Can I make a few comments before we disperse?
Yes, you can.
Yeah. I will like to thank and congratulate Dr. Martin Wieland for giving a very vivid picture of what may be the various effects involved in the safety of dam. He has very comprehensively illustrated the various problems with the existing dam which may be faced and timely actions are required. And also these will help taking care in advance for the new dams. So his speech and presentation was actually a feast to the eyes as well as the mind. And I am happy to inform that in India, we are now switching over to most of the things he has outlined. We are updating and modifying our guidelines. and his presentation would go a big way in educating the people involved in dam safety. So I will especially like to thank Dr. Martin for his efforts. Thank you very much.
Thank you very much, sir, for your compliments and for the detailed presentation of Dr. Will and Martin.
Yeah.
Okay, thanks a lot for your kind words. Yes.
Okay, sir. Thank you very much, sir.
Thank you.
Thank you.
Okay, thank you.